All right, so this is part 2. All right, guys, so this is part 2 of the lesson 3.3, which is dealing with momentum and impulse and collisions and explosions. We just got done with an explosion problem in 2 dimensions, and now we're going to get into collisions. So collisions are really the most likely place that you're going to use conservation of momentum in. And the key here is that a collision is just when 2 things run into each other. It's not overly complicated, but in all collisions, momentum is conserved. So you are always going to use conservation of momentum in your system. So your system is going to be whatever objects are running into each other, and then you're going to conserve momentum. So the total momentum in the beginning, which is what we started to do before. So the total initial momentum in either direction, X, Y, whatever direction it might be, in both, is going to be equal to the total momentum final. So when you add up all the momentum of all the pieces before the collision and you add up all the momentum of all the pieces after the collision, this has to be true. That is the law of conservation of momentum. So, and that you don't have any external forces. So in a collision, you just incorporate everything that's going to run into each other. It's also useful to think about Newton's third law, where it's the action-reaction pair idea. So like if you think about, and we have object A running into object B. If we think about the action-reaction pair, there's a force of A on B, maybe going to the right. The reaction to that would be the same equal and opposite force of B on A. So again, those have to be equal. And because they're equal forces and the time is the same, so that's equal. So there is an equal change in momentum. So the change in momentum of A is equal to the negative change in momentum of B. The reason why it's negative there is because they're directed opposite ways. So this one might be A is going to be positive and B would be negative because the forces are different directions. If you put that over to one side, if they're equal, then the change in momentum of A plus the change in momentum of B, and B is negative again, will get you 0. So there is no change in momentum as the key, and that's why they are the same. So that's the law of conservation of momentum as applied to collisions. So that's kind of what this diagram is showing you. All right. So there are 3 different types of collisions: elastic, inelastic, and perfectly inelastic. This slide kind of overviews them together, and then we'll talk about each one specific. Elastic collisions are called hard collisions, so because there is no deformation. So deformation is just when an object changes shape. And because there is no deformation, supposedly there is no kinetic energy lost. And the word lost is really not the best word to use because you can't really lose energy. We talk about that with conservation of energy. It just changes from one type to another. And lost is usually when we're referring to non-useful types of energy. So lost is when, like in a collision, when things hit, like I just clapped my hands, it makes sound, there's heat involved. And really in every collision, there's heat and sound involved. You can't have 2 things running into each other without that happening. But in these idealized situations, elastic, these are kind of ideal. We say that there is no heat or sound transfer, and all the energy is still mechanical energy. That's useful in maybe the kinetic theory of matter. That's probably the only time that I've ever heard about it in another science class. In chemistry class, you might talk about that. Elastic collisions, again, are used to model things. So it's not real, but it is a valid way to kind of look at it. Okay. Inelastic collisions, there are 2 types. So there's just regular inelastic collisions, and then I describe it as perfectly inelastic collisions. So inelastic collisions are the most common. These are the most common type. Most common type, deformation does occur. So things change shape. Kinetic energy is again changed or converted into heat or sound in that collision. Deformation isn't necessarily permanent. So deformation occurs when like you run into something. So imagine you're like walking down a crowded hallway and you bump shoulders with somebody. When you push on shoulder to shoulder, your shoulder gets pushed in, like there's like a deformation there, but it doesn't stay permanently dented, right? So like it returns to its original shape. So that's okay. That's deformation, and that would be inelastic. Perfectly inelastic, it's when it sticks together, and that's basically permanently deformed. So when objects stick together and become one object is essentially what's happening there. So again, kinetic energy is converted into heat or sound. All right. Perfectly inelastic are probably the simplest to consider, because you just have all the energy or all the momentum is going into one object. So you have two momentums in before, and then you just have one object afterwards. So you basically just add the masses. Explosions are the actual reverse of perfectly inelastic. So if we had object 1 was going to go to the right, and object 2 was going to the left, and they hit and stuck, if they had the same amount of momentum together, they would just stop here. And so this would be the initial, this would be the final. If you imagine this in reverse, if we started here as the initial, so these two objects are stuck together, and we played it in reverse, they would go the opposite ways. If we played the video in reverse, so 1 would go to the left, 2 would go to the right. That's an explosion. We kind of talked about that already. Okay. Inelastic, again, the most common type. Momentum is conserved. Momentum is always conserved. Always, always, always conserved. Kinetic energy of the system decreases. So the total kinetic energy, and so the kinetic energy initial should be greater than the kinetic energy final. And that is also true for, that's IE inelastic collisions. It's also true for pi, or perfectly inelastic collisions. So that's what happens when energy is converted. So like the total energy is all kinetic in the beginning, and it converts into non-mechanical energies. So in order to make it equal, you would have to add in the difference in those two would be the non-mechanical energy. And that makes sense, right? Because work was equal to the change in energy. And that's the non-mechanical stuff in this case. So tying it back into the ideas with energy. Elastic collisions, again, like I said, are idealized. Momentum is always conserved. Kinetic energy is conserved as well. So if you get the kinetic energy initial total of all the pieces, you add up all the kinetic energies in the beginning, and it's equal to the total kinetic energy at the end, then there is no transfer into heat or sound, and that makes it elastic. This equation is one that you can use for elastic only. So this is a specialized equation. It considers the velocities. It's basically called the relative velocity equation. So it compares the velocity of the first object before and the second object before the collision, and then after. So it's VAI minus VBI equals VBF minus VAF. Only works for elastic. The derivation of this is on the next slide. So like I take you through how this gets derived here if you are interested in it, but you just end up with this. This is all you need to worry about. And really you don't use it that much unless you have an elastic collision and it's given. Okay. So we're going to practice using that expression here and kind of take you through a conservation of momentum. All right. So we have this object A here in red, which has a mass of 2 kilograms and is moving initially at 6 meters per second going to the right. And we have the light blue object B, which is bigger, it's 4.4 kilograms, and it's going slower, it's going 2 meters per second going to the left. And we're going to solve for the final velocity of each object in this elastic collision. So we're going to use the equation VAI minus VBI equals VBF minus VAF. And we're going to use that in conjunction with the conservation of momentum equation. So those are going to work together. We're also going to check to compare the total kinetic energy initial and total kinetic energy final should be equal, because there shouldn't be any conversion of kinetic energy into non-mechanical forms. So let's just use this first. So the initial velocity here is positive 6. This is where the vectors are important. So we're going to subtract off negative 2 here. And that's equal to VBF, which we don't know the final velocity after the collision of B. And we also don't know the final velocity of A after the collision. So, so we have two variables in this equation. So this would be 6 minus a negative 2 would be 8. And I'm going to take this VAF to the other side, so it would be VAF positive plus 8 equals VBF. So that is one expression we're going to use to try to solve. And then we're also going to use our conservation of momentum one. So in conservation of momentum, if I go through that. Conservation of momentum says that the total momentum, so sigma p total initial, should equal the final momentum at the end, so sigma p final, so the total momentum final. And in the beginning, we have objects A momentum. So A has momentum, B has momentum, so we have to add them together. And then afterwards, they're going to have momentum as well because they're not sticking together. It's not becoming one object. So we have A and B momentum afterwards. So I'm just writing the A and B's, and now I'm going to put in the final for final afterwards, and then initial for before the collision. Okay, so as we go through this, it would be P equals mv. We're just using this basic equation in every one of these problems. So P equals mv, so it would be 2 times 6 for A, so 2 times 6 is positive 12. And then for B, it'd be 4.4 times negative 2, so that's going to be a negative 8.8. So that's the left side of the equation. On the right side of this equation, I have PAF, which I don't know the velocity, so it'd be 2 times the velocity of A final, plus B, which has a mass of 4.4, and I don't know the velocity of B final. So I'm stuck that I have 2 variables in this equation, and that's okay because we're going to have 2 equations. So 12 plus a negative 8.8 is 3.2. And then I have all the same letters on the right side here, so and numbers. So 2 VAF plus 4.4 VBF. And this is where that other equation is going to be useful. So that equation that we did up here, we're just going to substitute in this VAF in for VBF. So I'm going to take out essentially that VAF, and I'm going to plug that in there. So working through this some more, so I'll just move over to the left a little bit. 3.2 equals 2 VAF plus, and then we have this coefficient 4.4 because that's the mass of B, times this whole expression. So this is VAF plus 8. So all we did was substitute in this VBF into there. Okay, so when we do this and distribute the math, it turns out to be 3.2 equals 2 VAF plus 4.4 VAF, because I just multiplied 4.4 times that one. And then I also have to multiply it by 8. So 4.4 times 8 is 35.2. Okay, so then it's just grouping like terms. So I'm going to take this 35.2 to the other side. It becomes negative. So 35.2, negative 35.2 plus 3.2 just gets you a negative 32. That's equal to 6.4 VAF. And then it's just division by 6.4 on both sides. And you'll get VAF as a negative number. So that means that VAF bounces off and goes to the left. And you get negative 5 for that. So negative 5 meters per second. That is what VAF is. We can get VBF from just plugging it back in up here. So if I go up into here and I say, okay, negative 5 plus 8 should get me VBF. Then VBF is just equal to a positive 3 meters per second. So we have a solution for both of those, and we're going to check. I mean, you can plug it back in here and check it works in here. So it's the simultaneous solution, like it solves both of those. But we're going to go ahead and compare the kinetic energies. So the total kinetic energy, or sigma KEI, and this is a little bit of work again, but this is how you prove whether something is elastic or inelastic. So again, the kinetic energy formula, we haven't talked about it yet this video, is equal to 1/2 mv squared And you're going to do that for each piece. So it's going to be the kinetic energy of A before the collision, or initial, plus the kinetic energy of B before the collision. So let's go ahead and just do that math. So it would be, I'm going to do it on my calculator here. It'd be 1/2 times the mass of A. So the mass of A is 2, and then times 6 squared. So that's going to be 36 for that first term. And then for the second term, it's going to be 0.5 or 1/2 times 4.4 times -2 squared. And that's going to get you 8.8. So if we add those together, 36 plus 8.8, you get 44.8. Hopefully we will get 44.8 for the final total kinetic energy. No, it's not a good sigma. Let's try this again. So sigma KE final. And we got to think about, okay, well, what's moving at the end? We have both things. So kinetic energy A is moving, so A has a final kinetic energy, and B is also moving, so it has a final kinetic energy. And again, I'm going to just do the work on my calculator here. You can verify it using the kinetic energy equation, but you're just going to do this for each term. So 0.5 or 1/2 times 2 times the final velocity of A, which was -5, so that's 5 squared is 25. So that's going to get you 25. Plus, now we have to do it for B, so it would be 0.5 times 4.4 times 3 squared, which is 9, and that gets you 19.8. And this looks good. If we add those together, 19.8 plus 25, you get the same exact 44.8 joules. And that is proving, using these values, that they are equivalent. So if they are equal, it is elastic. So that's how we know that this is an elastic equation. It won't work any other way. So like if it's an elastic equation, this equation has to be satisfied. These are going to be equal. Conservation of momentum is the same in every problem, so that doesn't change. Okay. This one is not elastic, so we're going to figure out what type of collision it is. We're going to go through basically the same process. So we have a 5 kilogram object moving at 4 meters per second and a 1 kilogram object moving at 2.5. So this one's going to run into the back of B and kind of rear end it, and we want to know what's going on. It says after the collision, 4.5 meters per second, so that's VBF. All the stuff in the picture up there is the initials. And we want to figure out VAF. And then we're going to determine the type of collision by comparing the kinetic energies. So if you do this, the sum of the momentums before the collision or initial should equal the sum of the momentums final. So again, both pieces have momentum. So A has the momentum initially and B has momentum initially. And afterwards, they both have momentum as well. So PA, it's supposed to be an A, final, plus PB final. Okay. So, so if we do the math again, so for A, it'd be 20 times +4, or 5 times +4, which is just 20. And then 1 times 2.5 is 2.5. I'm skipping a couple steps here, but again, it's just P equals MB for each one of these. So we're just multiplying 5 times 4 to get 20 and 1 times 2.5 to get 2.5. So 22.5, that's the total momentum that we're dealing with in this situation. Afterwards, we know that the object for A is still 5 kilograms. It didn't change mass, but we're looking for VAF. So we're not sure what that value is. And the problem described that the 1 kilogram object is going at 4.5 meters per second. So you'd get 5 VAF plus 4.5. Again, you're just going to do algebra, so we're going to subtract the 4.5 on both sides. So you get something like 18 equals 5 VAF. And then you divide through by 5. I'm running out out of space. So let me scroll down. Divide through by 5. And you get VAF, which is the velocity of A after the collision, which is what we're asked to solve for in this problem, is a positive 3.6. So 3.6 meters per second. So the object, if you think about this, this object A runs into B. It's going to slow down, but it keeps moving to the right, and then B speeds up. So that's the idea. That's what should happen. For the kinetic energies, you're going to do the total kinetic energy, initial and final, just like we did in the last problem. So I'm going to skip ahead and just give you the answers that I got when I did this. But it's really just using the 1/2 mv squared equation for each and then adding them. So I got, for this one, 43.125 for the initial. That's how many joules you had to begin with A and B's kinetic energy put together. Afterwards, they don't really convert too much. Like they only convert 42.525 is the final. But you can see those numbers are not the same. So because the kinetic energy initial is not equal to the kinetic energy final, and it doesn't stick together, this is just a regular inelastic collision. Okay, so not too much left to go. A couple more problems just working through. I'm going to skip over this one just because I think we have enough other ones. Or actually, I'll do this one. I'll skip the next one. So it says this grandmother is roller skating with a mass of 80 kilograms, and she's going at 6 meters per second. And she's going to grab this stationary child and then wrap up, and they're going to move together. And we want to find out what their velocity is afterwards, and then how much kinetic energy is lost again. So again, it's just conservation of momentum. So this gets very repetitive. The total momentum before a collision should equal the total momentum afterwards. Now, this one's a little bit different because this person's stationary, so they don't have any momentum in the beginning. So it's just grandma's momentum. So it'll be 80 times 6, so that's 480. And afterwards, they're moving together. So if they're one object together, you're going to add the masses. So this is 120 VF. And then you divide through, just like we did in previous problems, by the mass to get the velocity. So the final velocity of them together is a value of 4, positive 4 meters per second. And that should make sense, right? So like this kid is obviously going to speed up because he's not moving and going to start moving. In order for him to speed up, grandma has to slow down. So she goes from 6 to 4, he goes from 0 to 4. And that's okay. That's the idea. So so that seems to check out and make sense. So that's your answer is positive 4. For the kinetic energies, again, you can do the work. I will show you the values, and then it asks you to find how much kinetic energy was lost. It's really how much is converted. So the difference in the energy is what you want to find. So kinetic energy initial, if you do that work for Granny and by herself, she has 1,440 joules. Together afterwards, the grandson and Granny, they have 960 when you do 1/2 mv squared for each one of those terms and add together. We want the change in kinetic energy. So change in kinetic energy, you subtract. And went from 1440 to 960, so you lose 480 joules. So that is the solution to this one there, negative 480. Okay. I said I'm going to skip over this one because we're running shorter on time than I want to do. This is just talking about two-dimensional again. So a car with a mass of 950 kilograms is going east. So object 1 is going east at some speed, and object 2 is going north at that speed. They want to know what, and they stick together, what's going to happen to them. So this is 1 and 2 together. So it's conservation of momentum. It's not anything too crazy. And you're asking for what's their velocity at the end. So you can work through this one again. It's not overly complicated. It's sort of like what we did in the first problem. You just do conservation of momentum for each direction. So in the X, and conservation of momentum final in the X. So the X direction saves momentum, and so does the Y. So you would have the same thing down here with Y's, and conservation of momentum final, and conservation of momentum initial. At the end, because they stick together, you have the total mass. So you divide the total momentum by the total mass and get the velocity of each piece afterwards. And then you would need to do trig to figure out with the x and y velocities to get the overall velocity and the angle and all that. Okay. Again, two-dimensional problems, you're just conserving in both directions, so before and after, that's what I talked about. They're independent of each other. So the x direction conserves whatever the x momentum is, and the y conserves momentum, and then you put them together to find the overall resultant momentum. All right. This problem I already have worked out, so I'm just going to talk through it really quickly. So this one, ball 1 runs into ball 2. Ball 1 scatters at an angle of 50 degrees. Ball 2, we're not sure about the angle it scatters at or the velocity, and it tells you information about the initial mass and velocity for each piece. So again, we're going to use conservation of momentum. I did it in the x direction and the y direction. You have two unknowns, so you're going to solve for like each of those velocities. So in the x one, you get 0.429 for the final velocity. In the x, for the 8 kilogram object. For the y, you get negative 0.383. Then you got to do your Pythagorean theorem, because you have, you know, like right and down, and you want the hypotenuse, and we want this angle. So on your slide, this is here, so this is the Pythagorean theorem part. I think I forgot to put this on the slide here. So this is the answer to the angle, and just showing you the inverse tan of that, and you should get 41.8 degrees below the positive x. It is not overly complicated. It's just repeating it for both directions and then doing the trig at the end. Okay, so I'll stop there and have a good one, guys.